Okay, let's get started. All right, welcome. Thank you for waking up at 8:30 to come to class. It's going to be an early class, so get some coffee before you come. Okay, so this is 377. I'm the instructor. My name is Prashant Shenoy, and I'll introduce you to the syllabus for the class today, tell you a little bit about how the course is structured. We'll do a quick introduction. It's going to be a shorter than usual class. So, and you will basically have some information you need to know for the rest of the semester. Okay, so let's start. As I said, it's an organizational meeting. So I'm going to start with the course organization, outline, syllabus, and so on. Okay, so the URL here shows you the course web page. So that's where I'm going to post some information on the page. There is also a Moodle page for the class. Whatever is on the web page will also get mirrored to the Moodle page. So if you follow one of the two, it should suffice. I usually post stuff on the web page. The TA picks it up and then reposts it to Moodle. Okay, Moodle is where you will turn in all your assignment. Everything is going to come in electronic except for exams, which will be administered in class. So you will turn all your assignments, homeworks, everything onto Moodle. I presume all of you know Moodle by now. Okay, so that's what we are going to use for the class. Okay. Core staff, the TA is Brendan. They swapped TAs a couple of days ago, so I just need to get confirmation that that is indeed the TA, which is why I put tentative there, but by and large I believe the choices are final. So Brendan Murphy will be your TA. I will get a picture of him if he doesn't show up next time and show you who he is, so you're familiar with what he looks like. Okay, there's going to be a grading staff person, Tim Simon, also tentative. You don't need to deal with Tim. For most practical purposes, you'll either talk to me or the TA. Okay? TA is responsible for leading the discussion sections on Friday. Okay? So I will work with the TA. We will prepare material for the discussion that will build upon whatever we do in the lectures on Tuesdays and Thursdays, and then on Fridays we will have a discussion section. Okay, so that's basically how the course is organized. Okay, so I presume all of you have taken 230. That's a prereq for this class. Spire wouldn't have let you in otherwise. Okay, so that knowledge of 230 is assumed. I will have some material to refresh your memory from time to time. Okay, basically you need to know a little bit about computer architecture. What little you learned in 230, what's a CPU, what are assembly instructions, and so on, because that is what an operating system will build upon. Okay? If you have forgotten some of that material, don't worry, I will have material to refresh your memory as we go along, but we assume that you know that material. Okay? Textbook for the class is the Silberschatz book. Okay, the book is in its 9th edition. From my practical standpoint, I don't think there is a whole lot of changes between even the 7th, 8th, and the 9th edition. If you find a cheaper copy that's an older edition, you can make do. There shouldn't be any problem. The newer material that they keep adding at the end, we never get to any. The earlier chapters don't change very often. Okay, so feel free to look at what works best for your budget. If you have the 9th edition already, that's fine. If you find a copy somewhere that's a little older, that should work just as well. Okay? I will put a couple of these books on reserve in the library if anyone wants to go there and look at the reference there. Okay? There are a couple of other textbooks. They are not required. I'm going to use them as reference books, and I'll also keep copies in the library. They have some good material also. Okay, I will be using them in the class, but you don't need to have the book. Okay? Just so that you know. But if you have access to them, do look it up. There are some useful material there. The two that we are going to use most frequently is Modern Operating System by Tannenbaum and Operating System by Dahlin and Anderson. A reference book not required. Textbook you should have access somehow. Okay? Either a copy of your own, somebody you are sharing with, or go to the library. Okay. As far as course requirements are concerned, okay, there is going to be exams, programming assignments, homework, and classwork. Okay, that's basically how the course is structured. Okay, so there will be several homeworks, around 5 to 6 homeworks that will be handed out time to time, and there is going to be some assignments we will do either here or in the discussion section. Okay. There's only a small number of points assigned to this, but that's a good motivation for you to get up and come to class, okay, because there could be a quick quiz every once in a while. Not every class, but every once in a while. Okay, that's around 15% of the total grade. Okay. The most of the grade is split between exams and the labs, which we call programming assignments. Okay. So there are 3 programming assignments. Each is going to be about 15% of the grade. Okay. And there are going to be 3 exams, 2 midterms and a final. Each of those are also 15% each. Okay. So 45, says 40 and 45, not 45 and 45. Okay. So exams are 13% each, assignments are 15% each. Okay, so every month there is going to be a test because we have approximately 3 months or so. Okay, so and then there is going to be approximately a lab also every month, September, October, November. Okay, if you have questions, you should ask. Don't wait until the end. Okay? Always feel free to raise your hand, ask questions for clarification. Okay, there are late policies that are spelled out in the on the syllabus page. You should look at them. Okay, typically, you cannot turn in things late unless you have a medical emergency or some sort of an emergency that needs to be documented for us. So you should make sure you understand all of that. Don't come to me 1 hour after the deadline saying something went wrong. Okay, that's often the wrong time to bring something up. Okay. Now, as far as the way the labs work, most of you have access to your own machines. Feel free to use it to work on your lab assignments and turn things in. Okay. You will have accounts on the EdLab. Okay. Most of you probably will not actually work there. Okay. So you will work on your laptop. But what you do need to ensure is before you turn something in, that it actually works or runs on the EdLab machines, that you haven't used some incompatible software or you haven't hard-coded some paths where we try to run it there and it doesn't work. Okay? Your assignments will be graded on the EdLab machines. Where you work on them is your choice. Okay? So make sure that if you use some compiler or Java, you are actually going to be compatible with whatever is on the EdLab. So long as it runs there and we can run it and grade it, you should be fine. You're not required to work there. Yes?
Should the EdLabs run Ubuntu?
Do the EdLabs run Ubuntu? At one point they used to run CentOS. I believe they still run CentOS. I'm not sure if this is to Ubuntu. The choice of the OS itself shouldn't actually matter as to what you use to write your code. Okay? So keep that in mind, but I will find out what they actually run. Okay. Discussion sections will, as I mentioned, do 2 things. Reinforce concepts we will actually cover here through small group work or assignments, and by and large they'll focus on lab assignments. Okay. Lab assignments will also build on course material. You will actually write programming assignments that require you to code up some concepts that you learn here. So in some sense, discussions always reinforce what's happening in the lectures. Okay, my office hours are always going to be after class, immediately after class. So if you have a question, you can immediately come up and talk to me. Okay, if you have other classes that present a conflict, I can talk to you at other times, but you will have to make an appointment. Okay, so right after class, I will have office hours. The TA will also have office hours. Yeah, mine will be on Mondays and Wednesdays. Oh, sorry, not Mondays and Wednesdays. That's incorrect. Tuesdays and Thursdays. So. Right after class, that's a typo there. The TA's office hours will be on Mondays and Wednesdays. Okay? That way you can see one of us on practically any day of the week. Okay, so I already mentioned programming assignment 45%, exams 40%. Okay, so keep that in mind. Now, as far as the labs themselves are concerned, it says 3 to 4. It's actually going to be 3 labs. Okay, but there is going to be one lab 0 that I'm going to hand out just so that you're comfortable with what is coming down the road. Okay? If you struggle with lab 0, you need to come see me. Okay? It may be that you do not have sufficient programming expertise to actually deal with the real labs that are going to come up. Okay? Lab 0 has to be turned in, but it will be graded, but it won't count towards your final grade. Okay? Because it's not a real lab, but it's something that you need to do as a prereq to all the other labs. Okay, projects that or the labs that you do will mostly be C, C++. There some may have some aspects of Java. Okay, I presume now most of you know C or C++ from 230. Is that correct? Okay, so until last year everything was in Java, but now that 230 has started providing C and C++ exposure, I'm going to go back and switch the labs back to C, C++. All operating systems are written in C. So it's somewhat awkward to do labs in Java when you're learning about operating systems. So we will go back to what is the natural language for writing operating systems and use C or C++. There may be some occasional things you have to do in Java, but I'm going to switch most of it back to C and C++. Okay. If you are not comfortable with it, I can provide some material that you will have to use to refresh your memory. Lab 0 again will help you do that a little bit. Okay. Oh yeah, the other important thing is you have to form groups. You don't have to, but you can. Okay, so we allow labs to be done in groups of 2. If you feel that you want to work on it by yourself, by all means, but do not start that lab late. You will soon find out that that's a mistake. Because the amount of work that is involved is typically much more than what you think it is. Okay, so if you work as a group, also you should start early. It's not a reason to start late and miss the deadline. But especially if you decide that you are not going to form a group, okay, labs will be given out 2 weeks before the deadline. Almost always nobody even looks at them until 1 week before the deadline. So don't make that mistake. Okay, try to start early, that way you will get done on time. Okay. You will have computer lab accounts on the EdLab, as I mentioned. They should be set up soon, okay, but you can use your own machines. That shouldn't be a problem. Okay. So there is a policy on plagiarism, as in all classes. Okay. I will require that you actually read the policy, sign it, and turn it in on Moodle, because we will strictly enforce it, especially for the lab. Okay. We are going to run automatic checkers that are going to compare your code with snippets on the internet with one another and so on. And these pieces of software are really good at flagging similarities in code and so on. So I would urge you not to go down the path of borrowing someone's code or doing something that is going to violate the policy. Okay, so you need to read it, understand it, and make sure you follow it. Okay? So that is why I require that your first homework is actually going to be turning in a copy of that policy that you signed that indicates that you actually read it. Okay? Okay, so cell phone laptop policy, okay, you do not use cell phones or laptops in class, okay, because cell phones are a distraction, laptops are also a distraction. Okay, you can bring paper and take notes. I'll put up the class slides the night before, you can print it and bring it here. Okay, because if you have a laptop open, what happens is you start doing something else, and then 5 people around you are looking at what you're doing, and half the class is so distracted. Okay, so I've decided that you will not use either laptops or cell phones. You shouldn't use in class anyway, but laptops as well, or tablets for that matter. Okay, so next time, I think you didn't know this today, next time when you come in, do not have your laptops open. You can bring some notebook or bring the class slides that I post to take notes. Okay, this way there will be better interaction. You should always ask questions and not get distracted with devices in class. Okay, so that's it as far as the syllabus is concerned. I'm going to pause to see if there are any questions before I do a quick introduction to operating systems. Any questions about the course organization, topic, books, policies, anything at all? Okay. So let me now spend the remaining maybe hour or less than an hour on a quick introduction to what the course is about. I'll tell you a little bit about what we build, what we mean by an operating system, and then a quick history lesson. Okay, how operating systems have evolved to what you see them as today. Okay, so broadly the topic course has 4 big topics. Okay, they are listed there. The first quarter of the course is going to focus on processes and threads, process and thread management. The second quarter is going to be memory management. Third one, I/O and storage. Okay? And the fourth one is going to be networking and distributed system. Okay? These are also the 4 key components of an operating systems. Okay? So those are the 4 big parts of the course as well. Okay? The book is also organized in that fashion. Each of those topics will have multiple chapters in the book, as you will see. But that's basically the 4 big topics that we are going to cover in the course. Okay. So with that, I'm going to now give you a quick definition of what is an operating system. Okay. So really there is no one definition. It has actually changed over the years. Okay. And people will define it different ways. Okay. A textbook may define it in one way. When you go to, let's say, Apple or Microsoft or Linux and say, I want the latest release of the operating system, what they mean by an OS may be somewhat different than what we will actually use as our definition. Okay? So the bare bone definition of an OS is it's the operating system kernel. It's the part of the system that is going to manage all the hardware, all of the other software processes that run on the operating system. Okay, but when you say I have a copy of Windows, it actually includes not only the kernel, but a lot of other components, including the GUI that is used by users to interact with the operating system or the machine, many other system processes and so on. Okay? So for the purposes of our class, when we say an OS, we actually mean the OS kernel. The kernel is what we will refer to as the OS, not everything else that comes with it. Okay, every once in a while we may go back to these other components and look at how they interact with the kernel. But our focus is to understand how the kernel itself is designed and what it includes and how it works. Okay? So with that background, here are a few other ways to define an operating system. Okay? One way to look at it is it's the interface between the machine and the user. Okay? So when you have your machine, laptop, tablet, phones, desktops, the OS is the piece of software that allows you, the user, to interact with the machine. Without the OS, you are actually left with pieces of hardware that are hard to work with. Okay? So it is basically the interface that sits between the two. Yes, question.
Could you just define what the kernel is?
Okay, I will come to. So the question is, what is the kernel? I'm going to come back to that in a little bit. Okay, so if you don't understand what that is, just hold off for a little bit. And there are some pictures, it will become clear what it is. Okay. So these are more general definition. Okay, the OS is the interface between the user and the hardware, which is the underlying architecture. Okay. Another way to look at it, it's that it is a abstract or a virtual machine, okay, that is easier to program than raw hardware. Okay. If you are actually going to start programming raw hardware, it's very difficult because you, the programmer, has to work with what are the hardware pieces, how they work with one another, and so on and so forth. Okay. But what the OS does is it presents an easier to use abstraction. Okay. It provides abstraction of processes, it provides abstraction of managing memory. The storage on hard disk is presented in form of files and file systems and so on. So these abstractions make it easier to write applications, use the application, and so on and so forth. Okay. Now I will note here that for those of you who have actually used virtual machines like VMware and Parallel and VirtualBox and so on, okay, what we mean by virtual machine here is somewhat different from that those virtual machines which are hardware virtual machines. Here a virtual machine simply means it's an abstraction. It's a logical machine that looks like a physical machine, but has different abstractions that you work with. Okay, so here are some pictures that now start making a little more sense. So as I said, it's the interface between the user and the hardware. Here is your operating system software layer. That's your hardware, bare bones machine. Those are applications. So the applications interact with the hardware through the operating system. Okay? And there's a question as to what the kernel is. It is the part of the OS, okay, that is actually going to work with the applications and the underlying hardware. Okay? It is the part of the OS, or I shouldn't say part of the OS, that's what we mean by an OS. It is the part, it's the system software that actually manages the underlying hardware and allows application to access the hardware. Okay? So there are many. These are some many other definitions. Okay, so OS is the system software that makes the machine looks faster, reliable. It even makes it bigger in some sense. If you have a limited amount of memory, for example, let's say you have 4 GB or 8 GB of RAM on your machine, when you have an OS running, it doesn't impose that restrictions on your applications. Your applications can actually use more memory than you have physical RAM. Okay, so your application, your OS makes your machine look bigger, at least in this respect, than it actually is. So there are many other neat tricks that the OS will allow us to play. Okay? Another way to think about it is the resource manager on your machine. It's the piece of software that manages all the resources, okay, whether it's the registers, the memory, the I/O devices. All of these are managed coordinated by the OS. If two applications need access to the same piece of hardware at the same time, okay, the OS is the piece of software that's going to arbitrate and decide which application gets access first and which one goes next. Okay? So it's a resource manager as well. Okay? Now, operating systems have a long history. They were first designed back in the 1960s, and they've evolved quite a bit over the several decades that have gone by since. As we will see in the history lesson, the functionality that they present to the user have also changed over time. Okay? And they continue to evolve. So by no means a mature field. As new forms of hardware come out, there are also operating systems that adapt to them. Okay? 5 years ago, there were no phone operating systems. Okay? Today, Android, iOS, and there are many others, are now versions of operating systems that have been adapted to phone hardware. So the same is true of things like the web, grid, cloud, data centers, and so on. These are much larger systems, and the operating system has to be able to manage much larger systems that span multiple machines, not a single machine. Okay? So if you can think of operating systems, they come in a variety of flavors. Okay? They could actually manage very tiny devices, okay, embedded hardware. They could manage your standard laptops, desktops, and related devices. They also manage distributed systems consisting of hundreds, thousands of machines and cores. Okay? So as you can see, there is no one way to design an operating system that will span the entire spectrum. Okay? Depending on what device the OS is meant for, you may have to make design choices. What do applications on that piece of hardware need, and how does the OS provide the desired functionality? Okay. By and large, here we are not going to look at embedded operating system devices, OSs that run on very tiny pieces of hardware. We are going to look at operating systems that run on standard desktop servers and laptops. Okay. We are also going to briefly touch upon OSs that span distributed systems, but we are not going to go into any depth there. And just to give you a flavor of how you need to scale up to much larger systems. Okay, so that's basically the scope of what is going to be covered in this course. Okay. There are also open source operating systems that allow you to actually gain in-depth knowledge of OSs. Okay, so if you have looked at Linux or FreeBSD or many other open source projects, you can actually look at the source and try to understand what those OSs do. Okay? Commercial operating systems, of course, you do not have access to the source code, so you have to understand them from the outside. But OSs allow you, open source ones at least, allow you to actually look at some of these in more in depth. Okay? Now in this course we are not going to go and look at source code for Linux kernels and so on. There's a different course that actually touches upon that, which is a follow-on course to 377. Okay, so we don't do that here, but do keep in mind that you can actually learn about operating system by looking at the source code, modifying it, adding new functionality, and so on. Okay, so I'm going to now, with that background or high-level definitions of operating system, I'm going to go and say a little bit about what are the features that a OS kernel provides, okay, how we can look at that from a perspective of an end user and end application. Okay. So an operating system provides a number of services to higher level applications or higher level system software. Okay. These services include storage services such as the file system, okay, which you should be all familiar with. Okay, when you store data on your hard drive, you store it in form of files, you organize files into folders. Okay. Now how that file, data in your file is actually stored on the underlying disk is something that you, the user, don't worry about, neither do your application. That's the task of the operating system. So you create a 1 megabyte file. It's the job of the OS to figure out where you put it on disk, where is free space that has 1 megabyte of free space, and how do you lay it out on disk. Okay, that the OS is going to do for you. Okay, so your job as the user or end application is much easier. You don't have to go and look at your hard disk to find the right amount of space and then put your data there. Okay. The same is true for all other pieces of hardware on your machine. Where memory is the same concept. Okay, when you start a new process, let's say you fire up your browser, okay, let's say you fire up Chrome, you don't have to worry about where Chrome is going to be loaded in memory. Okay, maybe you have 8 GB of RAM, you don't worry about which piece of memory or what addresses is the code going to be loaded. The OS deals with that. Okay. Again, your job as a user is simplified because you don't have to deal with it. Now, I say that you don't have to deal with it because in the early days of operating systems, you did have to work with those problems. Okay. The OS did not provide those services. You had to actually write code to say this program is going to load into this region of RAM and that's where it's going to run. Okay. Very complicated. When you have multiple programs, where do you put them, how big they are, and so on. Now, the OS does all of this for you. Your job is very simple. You just run your applications, do your work. The OS does all the underlying hard work for you. Okay, networking, same thing. CPU, same thing. Processes is the abstraction that you are provided for using your CPU cycles. Okay, your processes run on your cores on your machine. Okay, you may have multiple processes that may run on multiple cores. In what order do they run? When does each one run? All of this is dealt with by your operating system. You don't have to worry about, I run this application at this time and on CPU that is at some other application at some other time. Okay? So these are all useful services that the OS provides to us. Okay? And we are going to look at all of them, okay, in this course, okay, just as an example. Okay? The other thing that the OS does is coordination, and I briefly mentioned that earlier. Okay? Whenever you have resources that are used by multiple entities, there is going to be conflict and you have to arbitrate or coordinate. Okay? If two processes are both ready to run, which one is going to run next? Okay? So that's something that the OS is going to decide for you. Both cannot run on a CPU at the same time, okay, on a single core machine at least. Okay? So only one process can run at any given time. So the OS is going to employ techniques like scheduling. Yes, process scheduling rather, that decide how processes get scheduled. Okay? You have to ensure that there is fairness in the system. And you cannot let one process hog all of the CPU and other processes are starving. Okay? So you want to ensure all of them make progress, they get their fair share of the CPU and so on. Okay? And the same is true of many other devices as well. If you are, let's say, if you have two processes that are trying to use the network card on your machine, whether it's a Wi-Fi card or an Ethernet card is not important, but let's say both applications are trying to either send or receive data. Okay? How do you schedule that so both get the desired share of the network bandwidth and one process doesn't starve out the other? That's another issue of coordination or scheduling that the OS has to deal with. Okay, and so on and so forth. Security is also a service that the operating system will provide to you. Okay, it will prevent, so long as you set the right permissions on your files, other users will not be able to access the files. If you have the right set of abstractions turned on your machine, entities from the outside cannot access your machine and so on. All of these are OS services that the OS will provide. Okay. So the goal of this class is to understand how to design an operating system that will make all of those things happen. Okay. Basically, it will give you a machine that is convenient to use, okay, and also efficient to use. Okay. Convenience is a software engineering problem. If you are taken 320, you understand a little bit about how to design software so that it is easy to use. Okay, it's more easy to use, easy to maintain, easy to develop, and so on. Okay. So that is one important aspect because operating systems evolve over time. Okay, they are not static software systems. So you need to ensure that you can add new functionality and so on. So that's part of it is actually a software engineering problem. Efficiency is a systems and an engineering problem. Okay, you want a machine to be fast. You don't want it to be sluggish. So how do you make the OS or how do you design the OS so that it allows applications to run efficiently? Okay, that's another problem we are going to look at as well. Okay. And as you will see, sometimes these choices are not going to be easy to make. Okay. They will be conflicting choices. Okay. You can either go for efficiency or you can go for convenience. Okay. By adding more features to make it convenient, you may lose efficiency. Okay. What is the right choice is something that we will actually learn in this course. What are the right choices to make? Okay. It's something that we are going to learn in this course. And that's not just an OS problem. Okay. Anytime you design any large software system, you are going to be presented with trade-offs. Okay. There is not going to be one clear answer. Okay. You will have to decide which way to go. Okay. How do you make that choice judiciously? Okay. That's an important takeaway from the course. The course is as much about designing large software systems as it is about learning about operating systems. Okay. So we'll be presented with these trade-offs over and over again. And we'll see how many current operating systems have made their choices and what those trade-offs mean, what are the upsides and downsides of those choices. Okay. Any questions about this? Okay. So I mentioned some of this already. Okay. So abstractions I already said. How do you design an operating system kernel? Operating system that provides its users with an easy to use abstraction. Okay, we mentioned this already. I also mentioned this trade-offs. So there are many trade-offs we are going to look at. Performance and convenience, performance and simplicity, functionality and efficiency and so on. Okay. So through this course you'll gain an understanding not only of the OS kernel but also how to make some of these choices. Okay. And the last point I'm going to make is the OS is the layer of software where really the hardware and software meet. By software I mean higher level applications, and by hardware I mean the bare bone architecture on your machine. Okay, it's the point where these two are actually going to intersect. Okay, so it's an important software system from that perspective. Okay, so I already mentioned that you need to have a little bit of background on computer architecture to understand some of what is going to go on in operating system design. Okay, I'm assuming again that 230 has covered most of that background, and I will provide some refresher as we go along. Okay, so you need to understand what is a CPU. You should have at least heard of what is a CPU instruction set, what does I/O mean at a high level, and so on. And for the programming assignments, you need to know data structures and things like that, as you probably have learned those things already as well. Okay? Data structures, classes, and so on and so forth. Okay, so as I already mentioned, the course is as much about learning how to design large software systems. And the principles do not change. And what you learn here, you can apply to other software systems. There's probably a very little chance that some of you are actually going to go and build your own operating system kernel or be part of a team that will build your own kernel. There are not that many OS kernels that are under active development. There are only a small handful of them. So the reason you are in this class is the knowledge that you will gain, you can actually use to do other things that you are likely going to work on as part of your career on someday. Okay? These are other kinds of software systems, distributed systems, any software platform that is large and complex. These same kinds of principles will apply. Okay? So this is so these could range from distributed systems, grid, web, cloud. Some of these concepts you will touch upon at some point or the other. Okay? So principles here will actually help you build better software systems in general. Okay? So with that quick background, I'm going to delve into this history lesson. Okay? But I'm going to pause here just to see if you have any questions on what I said so far. Is your question answered about what is OS kernel?
Basically.
Yeah, so as I mentioned earlier also, by OS we actually mean the OS kernel here, and that's the underlying piece of software that is going to sit right on top of hardware, manage all the hardware and allow applications to use those hardware more efficiently. Sometimes there is not going to be a clear boundary between where the OS kernel stops and where the rest of the OS components begin, because as I said, to others, OS means more than the kernel. Okay? To us, it's going to actually mean just the kernel. Okay? So the OS will have components that sit outside the kernel. Okay? The GUI component is a good example. Okay? Both Windows and Mac come with their own GUIs, and those vendors consider some of those aspects to be part of the OS. Okay? To us, the GUI is not part of the OS. We are only going to focus on kernel design, not on GUI design, for instance. Okay. Are there any questions on what I've covered so far? It's a very quick high-level introduction. There's nothing deep that I said here. We're going to go and look at all of those topics in depth starting next class. Okay, so now we can look a little bit about how operating systems have evolved from the old days, 1960s, where they were used mostly for mainframes, to today where they are actually used for a vast spectrum of devices. Okay? There's even a car operating system that is under development, as you probably have heard of. Okay? So any device that has a processor needs an OS to manage that processor. Okay? So we're going to go from mainframe to web-based systems in about 9 slides. Okay? So we're going to start with the early days, which were single-user computers. Okay? Back in the 60s, hardware was very expensive. Okay? Buying a machine meant spending $1 million to buy a large piece of a mainframe, probably the size of this room. Okay? Didn't do much more than what, I shouldn't say couldn't even do as much as what today's phones can do. Okay? But that's what machines cost in those days. Okay? Labor, which means human programmers, were cheap as compared to machines. Okay? Programmers didn't make $1 million salaries. Okay? They don't make that even today. But machines cost that much. Okay? So you have to optimize for how do you take an expensive machine and make the best use of it using multiple programmers. Okay? Now OSs in those days, unfortunately, were what are called uniprocessor, single-user system. Only one user could access this big piece of hardware at any given time and run one program at a time. Okay? So there wasn't a whole lot of arbitration the OS had to do. There was one user. The user would submit one program. The program would run, okay, and produce some output, and the next user or the same user could submit his or her next program, or some other user would come along and submit their program. Okay? So you never had a scenario where multiple programs ran at once and there were conflicts and you had to do the arbitration. So the OS that ran on this mainframe was relatively straightforward. It had to manage resources for one program or one process at a time. Okay? So that's one thing. The other thing is because there's only one process running at any given time, okay, there wasn't any overlap between I/O and computation that the OS had to deal with. Okay? And I'll come to the next couple of slides and make it clear what we mean by overlapping I/O and computation and why that's a useful thing to do. Okay? Okay, the last thing is the user had to be at the console to debug. Okay, these mainframes were very, very painful to program. Right? You actually had to use this thing called punch cards where you have to type out the program and feed it in, and it would load the program, run it, and spit out some output. Okay? You didn't have any nice GUIs or mice or anything like that to program your machine. Okay. So now, given that you had one user at a time, and it took some time for that user to load a program and run it and then have it spit some output back. Okay, what was a better way to use the machine was to give a batch of programs and have them go one after another rather than user feeding one program, waiting and then feeding the next program and so on. Because any time that you waste between two programs, the machine is sitting there idle. Okay? You made a big investment. Spend $1 million, the company spent $1 million buying a mainframe, and you want to make the most use of it. Anytime it's sitting idle, you have spent money on something that's not being used. Okay? So to keep the machine busy all the time, one better way to actually do that is to still run one program or one process at a time, but feed them as a batch. Okay, you take a batch of programs, you load them all, okay? Each one runs. As soon as one is done, the next one goes. You don't have any time spent in between where you're actually loading the next job. Okay? So this concept led to this notion of batch processing, okay, which exists even today. You must have heard of batch jobs and so on. Okay? So batch jobs are simply a list of jobs that you submit as a batch and they run one after another, okay, sequentially. Okay? Still one process, okay, running at any given time. No conflicts between processes, but processes are running right after one ends, the next one runs. So we are making better use of the machine's resources. The machine is not sitting there and idling. Okay? So this led to the notion of batch processing, and OSs had to evolve to support batch processing. Still very rudimentary operating systems. Okay? But at least they made a step from having one user program at any of the machine at one time to running a batch of programs at any given time. Okay? The next step in the evolution was the ability to overlap I/O and computation. Okay, so what does this mean? So let's assume that you have actually loaded one program and it's a process. Okay? It runs for a while on the CPU. Okay? Then let's say it has to do I/O. Okay? It has to read or write some data. Okay? That's what we mean by I/O. Now when it's reading or writing data, the CPU is idle. Because the process cannot execute until the I/O is finished, trying to read some data and then act upon it. Okay? So the CPU is idle. Okay? And I/O, as you all know, is slow as compared to the CPU. Disks are typically much slower, and reading or writing to disks is much slower than executing an instruction. Okay? So now if your machine is idling, not the machine, the CPU is idling, while that process is actually doing I/O, how could you make better use of your machine? Is the question clear what the problem is? So you are running one process at a time. Okay, the process that is running does some computation and then goes back to doing I/O. Or not goes back, but starts doing I/O. While it is reading or writing data, your CPU is idle. And nothing is running on the CPU. So effectively, you have a slow I/O process that is executing, a slow I/O task that's executing, and you have an idling CPU. Can we now make better use of resources on this machine? And if so, how? Yes.
You can run instructions that don't depend on that data.
Okay, so you could run instructions that don't depend on that data. That is the right answer. Okay. But so in those days, there was no way, so programs were sequential. Okay. You run some instructions. If you have an I/O instruction, your process goes off to do I/O, there's nothing else you can run. But the right answer is if you don't want to keep the CPU busy, you want to run something while this process is actually doing I/O. So you run some other instructions, those instructions should be from another program. Okay. So now you can, this is what we mean by overlapping I/O and computation. So if some processes are doing I/O, let other processes that are ready to run actually use the CPU. So you make better use of all the resources on your machine. Some are using the I/O devices, others will be using CPU. Okay. This requires you to run more than one process at a time. If you have only one process and that process has gone off to do I/O, there's nothing else you can run. You want to now use the CPU, you have to load another process and run that process while the first one is doing I/O. Okay. Now this causes you to, allows you to overlap I/O and computation. They are both taking place at the same time, concurrently. Some processes are reading, writing data, another process may be actually running on the CPU at the same time. Okay. It allows you to make better use of your machine's resources. Okay. So this is basically this concept of overlapping I/O and computation. Okay. Now that concept led to this notion of multiprogramming. Multiprogramming simply allows you to load more than one process at once and run them all concurrently. Not at the same time, but concurrently. They are all loaded in RAM. The CPU will decide, I'm going to run application A for a little bit. Application A executes on the CPU. After a while, it will go off to do I/O, or it has to be told to relinquish the CPU. Then application B gets to run next, and then C gets to run, and then you cycle back, and A gets to run, and B and C, and so on. Okay? This is referred to this notion of multiprogramming, where more than one processes are loaded in memory, and they all take turns running on the CPU and doing I/O. Okay? So you have multiple applications loaded. Now, this is naturally true in today's operating systems, where you have a browser open and a mail client and your editor and so on. Okay? But there was a time when you couldn't do that. You could only run one application at a time. Okay? Now you can run as many as you want. They're all loaded in memory. So what that also says is today's operating systems are by and large multi-program systems. Okay? They allow more than one program to run at the same time, concurrently. Okay? If you have multiple cores on your machine, you will actually get real parallelism, and multiple applications will run on independent cores at the same time. Okay? If you have only one core, then they are all loaded in memory, but they take turns running on the one core that you have. In either case, you have multiple processes that are resident in memory, all active in some way. Okay? Is that clear? So that was the next big step in multiprogramming. Now, going from uniprogramming to multiprogramming is a big step from an operating system evolution standpoint. It makes the OS far more complex because there were functions that were not needed earlier now that come into play. Okay? You have to put in what is called a CPU scheduler that decides which process gets to run next. You need to have a scheduling policy. If only one process, there was no such decision to be made. That's the process that's running. Now, if you have 100 processes loaded, which one runs in what order do they run? All of these choices have been made by the OS. Okay? You also have to now put in a memory manager, okay, that manages the RAM across processes. It decides how much RAM to give to each process. Okay? It prevents one process from accessing another process's memory and trampling on it. Okay? That's called protection. None of these were needed when there's only one process running. You didn't have to protect that process from someone else or prevent that process from doing some harm to some of the processes. Okay? Now you have to put in a memory management system. Okay? And so on. So there are numerous additional functions that come into play. So from an OS evolution standpoint, this was a big step. Okay? From a user convenience standpoint, it just looks like, okay, we have one running, now we have N running. Doesn't seem like a big deal, but you have to, the OS becomes a lot more complex when you decide to allow multi-programming. Okay. Now, as the OS functions evolved, as I said, the complexity grew. Okay, to a point where there were some OS design projects that actually became so complex that they ended up as failure. They never actually managed to get the OS to run reliably. Okay. One such very famous project was this operating system called Multics, okay, designed in the 60s. Okay, they wanted to build this grand operating system that could do a lot more than anything that was available in those days could do. Okay. So they tried to put a lot of functionality into the operating system. Okay. This was probably the first large software system to be large, meaning a very complex software system to be built. I think they made a number of bad choices in terms of what functions to pick, the trade-off between functionality and performance. modularity of the operating system. So you make one change somewhere, it impacts 20 things somewhere else, and then lots of other things break. Right? You don't design a system in a modular way with the right interfaces, you are going to run into problems like this. Right? So there are software engineering problems, there were design choices that were not done well, and so on. And in the end, after spending literally millions of dollars and lots of programmer time, okay, the project went nowhere. They couldn't actually come up with a successful release, and they essentially canned the entire project. And then, it was actually a project that was the OS was designed by GE and MIT at that point in time. Okay. So they released it with many bugs. Nobody could run it reliably, and then nobody adopted it as a result, and it was of commercial and technical failure. Okay. So what that also says is making these design choices is important. You try to make things more complex than it needs to be, it actually backfires and your job becomes more difficult to make sure that the program actually runs and it is easy to maintain and so on and so forth. So having the right balance between functionality, convenience, simplicity, performance, all of this is very important. Okay. Now through that failure rose an operating system that is present even today, which was Unix, okay, which used a completely different philosophy. Okay. Multics was, let's put in lots of features and make this a grand operating system. Unix philosophy was keep it simple, okay, keep it bare bones. There is no need to add something if nobody has asked for it. Okay. So they started at the opposite end of the spectrum. They built this small operating system. In fact, it was built by only three programmers. And Multics had dozens and dozens of programmers. Okay. So three guys got together and built this OS that lives in some shape or form even today. Okay. And you can see the difference in design choices led to very different outcomes. Okay. So that's something to keep in mind as well. Okay. So that's basically what I was saying here. So there are other things that were going for Unix as well. Okay. So part of the reason Multics was so complex was it was designed for large, expensive mainframes which had lots of resources to manage. Okay. At the same point in time, technology evolution led to what were called mini computers. They were much smaller, cheaper computers than mainframes. Okay. They didn't have their own operating system in the early days. So what happened is these guys at Bell Labs, they came up with this operating system that they named Unix, okay, which was designed for smaller machines. It didn't have a lot of hardware, so they could design a simpler OS, but they also used a design philosophy that was very successful, which was keep it simple, okay, don't complicate things, go for performance, don't add functionality unless it's needed, and so on and so forth. Okay. So as I said, three guys built it in 2 years. Multics 10 years, dozens of programmers couldn't come up with any. Okay. So two very different design philosophies, two very different outcomes. Okay. Now with the rise of Unix, things have evolved quite a bit. Okay. This was still in the 70s, almost 40 years ago. Okay. So what happened is hardware prices continued to fall. Hardware CPU speeds continue to increase, disk sizes increase, memory sizes increase, and so on. Okay. So hardware kept getting cheaper. Okay. So in the 80s, we were actually at a different point in the evolution of operating system where hardware was very cheap. Okay. People's time was not. Okay. Hiring a programmer was still expensive. Programmers didn't become cheaper. Okay. But hardware did become cheaper. So what does that mean from an operating system standpoint? Because what this means is now rather than having a dozen people you share a machine, each programmer could be given their own machine, okay, which essentially led to the rise of personal computers or PCs. Okay? Because it was cheap enough to buy one for each programmer rather than spending $1 million buying one machine and having all your programmers go run their applications and get their output. Okay. So that led to large increases in productivity. Okay. If you have your own machine, you can do what you want with it in terms of programming and running your application. You don't have to share it with others. Each programmer has their own machine and so on. Okay. This also led to the rise of PC-based operating systems. Like the early ones were DOS, which has now grown into Windows, and Mac OS, which is still there, but in a different form as OS X. Okay. Now again, the PC-based operating systems went through the same evolution as mainframe operating systems. Okay. Early versions of PC operating systems were uniprogramming, much like early versions of mainframe operating systems. So if you have ever used DOS, you will know that you can only run one application on it at any given time. Okay. It was a uniprogramming OS, very simple OS, didn't provide protection. You make an error in your code, you could go and trample on the OS itself and take it down. Okay, which also led to the early rise of viruses. So there was no protection. You could go and corrupt the OS and take over the machine and so on. Okay. Now, as PC-based operating system evolved, it got the same features that server-based operating systems had, which is you could do multi-programming, you could get concurrency, you could get protection, and virtual memory and so on and so forth. And then eventually you basically had graphical user interfaces to interact with OSs, which made them really simple to use. You didn't have to sit on a shell prompt and type things. You could use a mouse to interact with it. Now with tablets, you use your hand and a touch screen. So all of these graphical user interfaces have made machines easier and easier to use. Okay. So now we are sort of in the 1990s and 2000s and so on. So hardware has become really cheap. Now you don't have one machine per user. You actually carry multiple devices that all have processors and run their own OS. Okay? You have a phone, you may have a tablet, you may have a laptop and so on. Because they are so cheap, you can afford to have more than one. Okay? You have various flavors of operating system because there's a spectrum of devices. You have different OSs for different devices. Okay, you have real-time operating systems. These are operating systems that run on really, really critical things. Like think of an airplane or a nuclear reactor, okay, where you have to get things right on time. Okay. If there is a delay, very bad things can happen. So many of these very complex physical systems are controlled by operating systems. Okay, these are very different kinds of operating systems than Windows and OS X. Okay? They are designed for very tight timeliness constraint. Tasks take a fixed amount of time. Everything in that system is predictable. So things happen at the right time. If they don't, then as I said, you can have critical failures and catastrophic problems as a result. Okay? So that is an entire area called real-time operating system, which we will not touch upon here, but you should know that they exist. Okay, they are real-time kernels that are designed for very critical things that have timeliness constraint. Okay. You have sensor and embedded operating systems. These are operating systems that run on devices that are not really computers. Okay. Think of a car or any device that's embedded that actually has a processor on it. Okay. You can buy cameras with things soon. You can buy smart watches with operating systems. These are all embedded operating systems. They run on devices that are actually not computers, but they are used for other purposes. Okay. So they also required different design philosophies from more general purpose operating systems. Okay. And then you have parallel and distributed systems where the OS has to manage more than one core and more than one machine. Okay. A distributed system can have tens, hundreds, or thousands of machines. The OS has to manage all of those resources. Can have parallel systems with lots and lots of cores. Again, the OS has to manage all of those cores. Okay? The design choices and the policies that are used in those flavors of operating system are different from what you may have on a laptop or a desktop or a server or a simple server. Okay, so that's basically the history lesson. And if you just look back as how things have evolved, you will see that what we have seen over the past 50 or so years is about 9 orders of magnitude improvement in technology. Okay? That's a very rapid pace. That's not 9 times, not 9x. That's 10 to the power 9, okay? Which is a very dramatic improvement in CPU speeds and memory sizes and things like that. Okay? So, and operating systems had to keep up with that pace of evolution. Okay? There's almost no other field of technology where things have actually evolved at this pace. Yeah? And this is here is just 2 columns showing what typical machines in 1983 looked like, and this is now 15 years old, but still is quite instructive. 1999 what it looked like. So you had, let's say, a disk in those days, a hard disk barely could store 1 gigabyte of data. Okay, 1 gigabyte was a lot. Okay, I remember disks that could hold 20 megabytes of data. Okay, that's not memory, I'm talking about hard disk and files. And now you can buy a terabyte disk. Okay, that was gigabyte, 1,000 times increase in storage capacity. Same with memory. Your RAM was actually 1 megabyte. Okay? These days, even caches are bigger than that. Forget RAM. Right? So now you have RAMs in gigabytes. Those days RAMs are in megabytes. Okay? Cost has actually reduced from $100,000 for MIP to $500. Okay? Cost has plummeted. Speeds have gone up. Okay? And OSs had to keep up with all of this. Okay? You can't have a static software system and the hardware is changing so quickly. Okay. So the other history lesson to take away is that the pace of technology evolution, okay, the sort of hardware evolution and OS evolution is like no other. Okay. If you look at two other fields, transportation and communication, okay, you will see that computation is still has had seen much bigger or much faster evolution. Transportation, you can see, we've gone from 10 miles an hour transportation to maybe 1,000 miles an hour. And take horse carriage to airplanes. Yeah, so that's 2 orders of magnitude improvement in maybe 100, 200 years. Okay. Communication is somewhat closer to computation, okay, but still not the same. So you have had kilobits networks, now you have terabyte networks. Okay, so if you have dial-up speeds, you are in kilobits. Now you can do terabytes. Okay, that field has also seen similar evolution because computation and communication are somewhat related, but that's still only 7 orders of magnitude. Here we are at 9 orders of magnitude. Okay? So big changes over the years. Yeah, and we have had, so that's a good thing to take away. So this is a pictorial depiction of, if you take a picture and zoom out 10 orders of magnitude, what you will see. So if that's your original picture and you keep zooming out, you will see what 10 orders of magnitude mean. That's just 1 order of magnitude. Okay, factor of 10. Okay, this factor of 100. Okay, that's 1,000. I don't even know where the original picture went. Okay, so that is the green is the original picture right there. Yes, so you'll see that the green is going to get smaller. That's 3. That's 4. That's 5. You can no longer see anything. Now you can see Florida. And now that's 7. That's 8, and that's 9. Okay, so that's basically from a pictorial standpoint, if you zoom out 10 or 9 orders of magnitude, that's what your thing will look like. That's basically how much more you can cram into one picture that you could do from the original picture. Okay, just a pictorial depiction of what this means. Okay, so we are more or less done. Here are some takeaways. Okay, so this technology evolution is also referred to as Moore's law. Anyone here heard of Moore's law? What is it? I have to put you on the spot and ask you what it is.
It's the idea that computer power and memory is going to double every 2 years.
So Moore's law is not really a law. It was an observation made by Gordon Moore, who founded Intel. And basically, he just put a simple rule of thumb on how quickly technology was evolving. And basically, what he observed was every 2 years, things were doubling. Right? Either your processor became twice as fast, or the size of your processor shrunk by half, each one is quarter. Okay? So that was a technology observation, and that has held for over almost 50 years. So every 2 years, so it was very common to see every 2 years speed double. Okay, and then you could buy a processor that was twice as fast. Now what has happened is Moore's law hasn't gone away, but some other problems have cropped up. The reason you're not seeing every 2 years the speed of your processor is doubling is because when you increase the density of your electronics, the heat that it dissipates also increases. Okay, so unless you are willing to burn real holes in your machines, you cannot actually keep doubling the speeds without dealing with the heat problem. So what they have started doing now is cramming more cores rather than making the processor faster. Because you have more room on the chip is shrinking. So if you want to keep the chip size the same, you can pack more electronics. Okay, so rather than making it faster, you are getting more cores. Okay, so you are basically now you can buy 16 core machines, and your phones have quad cores now. Which I don't know what you do with 4 cores on a phone, but you can get 4 cores on a phone. Okay, so that basically is what Moore's law is technology evolution allows you to shrink the size of electronics by half every 2 years. That effectively means either you can have electrons that are twice as fast, or you can have 4 times as much capacity on your chip. Okay. That is what has led to this exponential increase in sort of speeds and so on. Okay. So that's so all of what we talked about the history lesson is sort of another way to sort of look at Moore's law. Okay. So now that doesn't stop technology evolution. You have multiple cores, you have unreliable memory, heat power constraints we'll look at a little bit, and then there are reliability issues and so on. So interesting new technology concepts. Okay, so that's, I don't know what, that was just an old picture. So this was just Bill Gates with this early, a sleazy looking picture of Bill Gates with his DOS release from a long time ago. Okay, so anyway, this is where we will end it today. Okay, as I said, if you have questions, come talk to me. I will have other information for you next week about labs and so on.